Hello, Chem 115 students. It's time to talk a little bit longer about molecular shapes. I realize that the slide at the end of class today did not get notated as was intended, so I'm going to make sure this has been reviewed and filled in for you. Whenever you have two electron domains and no lone pairs, as we discussed in class today, whoops, let's go back. The shape of the molecule is going to be linear, and the bond angles should always be 180. That's the expected bond angles. You don't have to know about any that aren't. When you have three electron domains total with no lone pairs, then you should have the electron domain geometry. The shape is going to be a trigonal planar geometry with 120-degree angles, and that would be the expected angles. There are times there will be distortions, but those are not something you need to be expected to understand. Sometimes you'll be able to explain them when you see them, but don't worry. So if you have three electron domains total, the bond angle is always going to be 120, but if one of those electron domains is instead a lone pair, then the shape of the molecule becomes, as we mentioned in class today, only a bent shape, because instead of having three things around the central atom, you have two atoms and one lone pair, which gives you a result of a bent shape. When there are four electron domains total, the bond angle, the expected bond angle, is that 109.45, let's just say 109-degree angle, close enough. It's more than 3 sig figs is plenty. And so each of the other ones that have four total electron domains will likewise have a similar number of bond angles, though the latter two will have some distortions, and they will end up to be less than 109 because of those lone pairs, but that's all right. I'm not going to ask you to be specific there. And so the one below that is likewise less than 109. Now, the geometry, the molecular shape with those ideal bond angles of 109 when there are four electron domains and no lone pairs is described as, new word of the day, tetrahedral. When you have four electron domains and one of those is a lone pair, it no longer appears as a tetrahedral shape, but instead, if you go back to the previous page in figure 2, you result in what's called the trigonal but no longer planar trigonal pyramid shape. When there are four total electron domains, but two of them are lone pairs, and we'll look at more examples with this in a minute, then you have only two atoms attached to the central atom. If the bond angle is in that tetrahedral electron domain geometry, we end up again with something that is described as a bent molecule, or like a boomerang if you wish, but it's going to have 109-degree angles, unlike the previous example on this chart where the angles were a larger value because there were three electron domains in that example. So it depends on how many total electron domains you have. All right, now in view of the challenge that many of these problems present to students, I would like to work you through some of the exercises for a change today. The Lewis structure for NH3 was provided, and so let's talk our way through it. We had a structure where you had nitrogen in the center, and it has its three hydrogens, one on each side and one on the top or bottom as you choose. I'm going to put mine where it's convenient for this particular space, and that means I'll just lay it on the lower side. The Lewis structure included a single bond between nitrogen and each hydrogen, and then in addition, in order for nitrogen to have an octet and for us to account for all the electrons that should be in this structure, should be a total of 5 electrons for nitrogen plus 3 more for the hydrogens. Oh boy, the tool's not writing well today. For a total of 8 electrons, and that is reflected in this Lewis structure. And so in order for that to be true, this kind of structure fits. How many electron domains does the nitrogen atom have in the ammonia molecule? Again, each bond counts as one domain, so does the lone pair, and so that ends up with a total of 4 electron domains. And so looking at the chart we just completed in exercise 1, we can make a sketch of the electron domains. This will be the one where we have 4 electron domains and then 1 lone pair, because a nitrogen has a lone pair in this case. The idea is to draw something resembling what was shown in this chem activity, and it requires a little more skill than sometimes that you're otherwise going to use, but here's a way to do it. You think of it drawing with one bond going straight up. We'll make 1 hydrogen going there, 1 at kind of an angle to the lower right, and 1 of the hydrogens there. And then we have 2 other bonds, or 2 other electron domains, to say them more carefully. And one of these electron domains is shown with a dashed line to represent the fact that it goes behind the paper. I'll put 1 hydrogen there. And the remaining one will be represented as behind the lone pair. Now, that might not have been your first choice of way to do it, but this is one way of representing the trigonal pyramid geometry for a molecule with 4 electron domains and one of them being the lone pair. If I had done it a different way, I could also have shown it in a fashion you might have liked better. In the vertical position, I could have put the lone pair electrons there, which would have been more consistent with the Lewis structure I began with. 1 hydrogen on the lower right, and 1 hydrogen on the wedged bond, which represents one coming towards you, and then the remaining hydrogen suggested to go behind the plane of the paper with that dashed bond, and that would be shown that way. So that makes the kind of drawing that gives you this trigonal pyramid kind of shape. Trigonal pyramid. Okay, let's look at another example from the exercises, and this would be question number 3. Lewis structure for CH4, namely methane, is quite simply shown with a carbon, 4 hydrogens, and 1 bond to each of the hydrogens. That gives you an octet for carbon, and the complete outer shell, namely only 2 for each hydrogen. Not a tricky one to draw. Again, the question that you look at in deciding this, so this is how you do molecular shapes. First, you draw the Lewis structure. Then you determine the number of electron domains. And in this molecule, we have 4 electron domains. And then you examine the drawing, the shape, and figure out what kind of geometry this is going to be. Again, 4 domains, no lone pairs. We should have the same thing as we had on the previous example, where you put 4 bonds around the carbon in that interesting 3D representation. Remind you that nothing is really quite like it shows over there in the left with the Lewis structure. It's not 90-degree angles at all. And this type of thing represents the tetrahedral geometry and the approximate bond angles. The approximate bond angles for this then are about 109. Oops, let me make a correct symbol here. 109-degree angle. Not that you have to be precise any more than that. Okay, there's the name. It's called a tetrahedral molecular shape. And we'll go on to number 4. The Lewis structure for SO2 was already shown at the end of activity 13 the other day. Am I got the right number there? 13. And we will represent that without further description, just to tell you that it had a double bond to oxygen on one side, it had a single bond to oxygen on the other side, and in order for all the octets and the correct number of electrons to be shown, the resulting structure will have a single bond to oxygen on the one side with 3 lone pairs. The other side with the double bond will have 2 lone pairs on oxygen, and then a lone pair on the sulfur. That ends up with the proper number of electrons for this structure, which is a total of 8 and 8. With 16, 18 electrons is what you should have with this thing. With an oxygen and 1 sulfur, each of them brings in 6 electrons. There should be a total of 18 electrons. Now, having shown the Lewis structure, how many electron domains does the sulfur atom have? So this is the first thing. After we draw the Lewis structure, we can determine the number of electron domains. And so the second step gives us the way to think about this. When we have 2 bonding regions, namely 2 bonding domains, plus one lone pair. That is a total of 3 electron domains. The electron domains this time are going to be drawn differently. 3 electron domains are always going to have a trigonal geometry with 120-degree angles. And in this particular case, we have 2 oxygens on 2 of the bonding domains, the 2 bonding domains. And the third domain is just a lone pair. And so it's going to be influencing the geometry because it is a lone pair, and it is an electron domain. And in so doing, we end up putting it into a more realistic shape. And we have our 2 lone pairs on the oxygen. Where you put those on the oxygen isn't critical. And whether I put it on the left or the right with a double bond is also arbitrary. Just the question if you're looking at it frontwards or backwards. And so the other oxygen is going to have its 3 lone pairs. And making a drawing for this one, the electron domain geometry is different. It's not like the one that we had with tetrahedral things prior. And so the shape of the SO2 molecule with 2 bonding regions and 1 lone pair is now just simply the bent molecular shape. Again, bent molecular shape can arise when you have 3 electron domains with 1 lone pair. So 1 lone pair gives you that bent geometry instead of something that it might otherwise be linear. Lone pairs are very important to understanding molecular shape because you won't get the shape right if you leave them out when they're supposed to be present. All right, let's do another example. Oh, the bond angle already checked. Got that. Made sure I made that note of that. All right, there's a significant number of challenges on exercise number 5, so let's talk through a couple of them. I believe we've already done CO2, so let's let that one go for today. Let's do pH3, which was sketched out in your previous activity last week. And we had phosphorus with its normal geometry, it's 5 valence electrons and then 3 more for each of the hydrogens, results in 3 single bonds and 1 lone pair. And when you have 3 single bonds and 1 lone pair, that gives you 4 electron domains total. And one of them is obviously not a bond to an atom, and so there's 1 lone pair. And so using that information, that tells you that whenever there's 4 electron domains, the angle should be 109, thereabouts, close enough. And 1 lone pair means it's not tetrahedral, but instead this would become the trigonal pyramid geometry. This is very much analogous to the NH3 molecule. And so we could draw this one with a more realistic shape to represent the trigonal pyramid. And in order to do that, we'll use the wedge and the dashed line again to represent the different shape of the different perspectives. And so I'll put the phosphorus here with 1 bond, or 1 electron domain to the top, 1 to the right, 1 with a wedged bond, and 1 with the dashed bond. So I'll put 1 hydrogen over on the dashed bond, 1 on the wedge bond, 1 on the one to the right, and the remaining electron domain is only a lone pair, and that should look like a trigonal pyramid now, we hope. Okay, that was 1. Let's try then to do one that's a little bit more challenging, namely the SO3 minus 2 ion, namely sulfite. Sulfite is challenging because you've got an ion now, and this one gives us an excuse to talk through a Lewis structure. So SO3 minus 2 sulfite is going to have its Lewis structure determined first, step 1 every time. The total number of valence electrons is where we always begin. And if you think about sulfur and its 3 oxygens, the total number of valence electrons, oh boy, my tool is getting tricky on me again. The total then is going to be 6 for sulfur, and 3 oxygens are also each 6, so 3 times 6 more. Those are a total of 18 plus 6. But don't forget you have to have a couple more electrons for the charge. So if to add 2 more electrons to the whole picture to be complete, and that means we'll have to have 18 plus 8, which is 26 electrons, something different. All right, now, the arrangement of atoms. Again, the central atom is usually the one that's first listed in your formulas, unless it's hydrogen. And so we'll put sulfur in the middle. It's always a good way to start. And then think about symmetrical arrangements past that. Symmetry is very common, and so that's what we will expect to see. So put 3 oxygens around here, and let's follow the steps to making a Lewis structure. So the first thing to do after you decide how to lay out the atoms and who must be in the middle, which atom, is to make some bonds. And so we'll put in 3 sets of dots for a total of 6 electrons in those bonds, leaving us with, well, guess what, 20 electrons remaining to fill out the diagram and make it correct. Okay, so after we've made bonds, then we fill up octets on non-central atoms. So that means we're going to put 2, 4, 6 on each oxygen. And in doing that for 3 different oxygens, well, do your math. 3 times 6 should be a total of 18 more electrons. Give me a second, we'll get them all drawn in here. We'll call this chemistry dot to dot. And when we put those lone pair electrons in, there's only going to be a couple left to draw, and that would be 2. 2 more electrons. Okay, so the oxygens are filled up with octets. The only place left to put anything would be on sulfur. And if you look at that, that should give everything an octet. And in the case of drawing a Lewis structure for an ion, I mentioned this in class, it is proper to represent it with a charge around outside the brackets to represent the idea that every atom in there together has this charge of -2. Well, how do we draw the geometry for this one? Is this one going to have the same procedure? We'll figure out how many electron domains, and if you're looking at this diagram, the number of electron domains, and my tool doesn't want to write, is very similar to something we've seen at the top half of the page, top half of the screen here. And so if you've got 3 bonds and 1 lone pair, that makes a total of 4 electron domains. The number of electron domains tells us then the bond angle should be 109 approximately degree angle again. In other words, tetrahedral electron domain geometry. But when in this case, just as we had in the one at the top of the page, when you have 1 lone pair and 4 electron domains, we should get, once again, trigonal, pyramidal, trigonal pyramid kind of geometry. And so in order to draw this correctly, to represent that shape, I'll draw it over here to the right. We'll put the sulfur again in the middle. We'll put 1 bond this direction, 1 electron domain here. I'm going to go ahead and put the lone pair there to make it look a little more easy to recognize. Oh, that's supposed to be oxygen. And 1 bond coming towards you, 1 bond going away from you behind the plane of the paper, or the screen, wherever you're looking at it. And so 1 oxygen on each of those. Well, those are really funny looking oxygens. You've got to use your imagination today. And so that gives you the sulfite ion. And again, correctly shown, this whole ion has a charge of -2, or 2-, however you wish to state it. Either way is correct. All right. So it's the same thing as I wrote at the top of the screen, trigonal pyramid. Let's do, what more can we like to try? We've done those other ones. Let's do hydronium, and perhaps we should do the one that's hidden momentarily there behind that tool is H2CO. I believe this one is shown in the table 1 from this activity, so I won't draw that one today. So H3O is called hydronium. We need to come up with the total number of valence electrons to begin the Lewis structure. And so the total number of valence electrons is determined very simply as usual by counting up the valence electrons for the atoms included here. So we'll have one hydrogen electron, and wait a minute, there's 3 of them. So multiply that times 3. And then you also have one oxygen, and it has 6 valence electrons, just like oxygen always was. Now, when there's a positive charge, what does that mean? It means that we have more protons than electrons. In this case, we lose 1 electron from the total, and the total number of electrons is not 9, but 8. Oh, that could be an octet. So let's draw the Lewis structure. Guess what goes in the middle? Can't be hydrogen, so it better be oxygen. And this hydronium ion has a charge, so I'm going to put that charge on there before I finish. And to figure out the Lewis structure and do it in a complete fashion, we will start by making bonds. And 2, 4, 6 electrons go in the bonds. Well, that one got lost in the hydrogen. And so that means we've used up 6 electrons so far in just making bonds. There should be 2 more in the diagram to be correct. And hydrogens can't take more, so the remaining electron better go on oxygen. The charge again goes on the outside of the bracket now that I've finished it. Oxygen has an octet, and the correct number of electrons are shown, so the diagram should be complete. Again, we have 4 electron domains. And when there are 4 electron domains, this is feeling like an echo, and 1 lone pair, we got the same kind of pattern we've seen in 2 examples already. And so 1 lone pair results in, we'll have an angle of 109 approximately, close enough for our purposes, degrees, but it's actually less because of a lone pair, it's okay. And with that lone pair in there, the geometry becomes not tetrahedral, but this time trigonal. Which kind of trigonal? This one is the trigonal pyramid. And so trigonal pyramid should look familiar now because I've already done more than 2 examples for you. So trigonal pyramid has 3 bonds and 1 lone pair. Doesn't matter if it's an ion or a molecule, the shape of the molecular ion in this case is determined the same way as when you did molecules. Molecular ions are kind of a funny concept. They really are, the whole cluster of atoms together has that particular shape and a charge. All right, now let's do one more. I want to do the H2CO, which is a compound that you wouldn't learn until you get to Chem 116, so you don't have to worry about what it is. And when we start this, we'll start out by counting up the valence electrons and coming up with a correct Lewis structure. Lewis structure is step 1, and after that, you sketch the molecule to figure out the shapes and the bond angles and see where it takes you. All right, so total number of valence electrons. Let's see, 2 hydrogens, 2 electrons each, plus how many from carbon? Carbon has, 4 valence electrons, got it. And 1 oxygen, it's going to also have the same as its group number. Oxygen still has 6. So that would be a total of 12 valence electrons. You like this kind of math? Not too hard. And so 12 electrons need to go in the diagram in order for it to be complete. So, which way should we arrange the atoms? Well, this one isn't so complicated. Again, the atom closest to the center of the periodic table, not the first one in the formula in this case, should go in the center of your diagram. So let's put carbon in the middle. Carbon likes to be in the middle. It's very ordinary for it to be there. And we'll put some hydrogens where they can be bonded to carbon. That seems logical. They've got to be all connected here. And oxygen also has to be connected. And you kind of arrange them in a rectangular fashion around carbon because we're thinking in terms of octets. So for the 12 electrons, we begin by making bonds. And the bonds will take 2 and 4 electrons to connect, and then 6 more, total 6, to make sure that everything is connected by a bond to the central atom, leaving us with, wow, there you go, simple math, 6 more electrons. Guess where they go? Can't go on hydrogen. We won't do the last central atom until last. That's an important step in doing Lewis structures and getting them correct. And that putting 6 electrons on the oxygen in the lone pairs means that it's all used up. That's what we're using, but subtracting there for the lone pair. And the first one was the bonds. And that leaves no more electrons to put in the picture. That's supposed to say bonds. Use your imagination a little bit. Sorry, folks. This tool is very curious. Okay, no more electrons to put in the picture. Do all the atoms have an octet? Well, hydrogen never gets one. Oxygen has one, but carbon is deficient. So again, this is the kind of case where you have to remove or reassign electrons from oxygen from being a lone pair to being a bonding pair. Reassigning them means that oxygen keeps its octet, but this makes a double bond. And the double bond between carbon and oxygen still gives carbon the correct number of bonds, which should be 4, so 1 to each hydrogen and a double bond to oxygen. We can redraw this in a molecule shape if we think about the number of electron domains. So the number of electron domains in this case is the number of atoms attached plus the number of lone pairs. Well, how many lone pairs are on carbon? None. So the electron domains are 3, and the 3 electron domains gives you the bond angle. Every time you have 3 electron domains, the bond angles should be essentially 120 degrees. There is a little distortion from time to time, but that's okay. And 120 degree angle, what is the molecular shape? With 3 electron domains without lone pairs, this gives us the shape that we call a trigonal geometry, but more specifically, it's going to be trigonal planar. Drawing that geometry for this molecule in the space that's provided here, which is getting a little crowded, means that we simply put these things equally spaced around the carbon atom. I'm going to put lines for bonds now because it looks a little better. And so we'll put these things in a trigonal geometry. Think of how this would be like the hands on the clock being at, I'll pick the funny way to do it, being at 3 and 11 and 7 on the clock. That would be equally spaced. You could think of 12, 4, and 8 on a clock. That gives us the trigonal geometry. Let me draw a line in here to make sure that this isn't getting blurred in with my Lewis structure. And so how we represent the lone pairs on oxygen is not going to affect the way the overall shape looks, but there's your trigonal planar geometry. All right, that gives you some more examples with Lewis structures and geometry. I encourage you to practice as many as possible. The more you do, the more sense they make, I think. Now, the last exercise here is worth a few minutes of discussion. Predicting the bond angles around each atom designated with an arrow in this amino acid, not that you have to know anything about the molecule, requires understanding the number of bonds and the number of lone pairs. So the first arrow, we have 3 bonds around nitrogen and 3 bonds, but nitrogen, in order to have an octet, still has to have 1 lone pair, and that lone pair plus 3 bonds means that the total bond angle around there is going to be reflected by or influenced by the 4 electron total domains. And whenever you have 4 electron domains, the angle is going to be the same thing. It's the approximately 109 degree angle. So all they're asking here is the bond angle on that particular one. In this particular nitrogen atom, is what I'm referring to first here, is this geometry going to be tetrahedral with 1 lone pair in the 109 degree angle? Nope, not with a 109 degree angle. Nope, not that. So it won't be that. It's going to be instead the trigonal pyramid again. This is actually a very common geometry for nitrogen because nitrogen commonly has 3 bonds and 1 lone pair. Even though nitrogen is just one portion of this larger molecule, you can describe the geometry around a particular atom with the same kinds of things we use describing entire molecules. Okay, the second one is this carbon in the middle, and the carbon in the middle has, I'm going to label it. Carbon is example number 2 here. So number 2 is the carbon that has how many bonding domains? Well, it's going to have 3 bonding domains because there's 3 atoms attached. And in this case, it's 2 bonds in one of those domains, but that's all right. And bonding domains for 3 means that you're always going to have the same angle, which would be the 120-degree geometry. Again, with 120-degree angles, this is what we call trigonal or trigonal planar, more specifically, geometry. Flat, like 12, 8, and 4 on the clock, or if you'd rather do 10, 2, and 6, same idea. But trigonal planar is a very flat geometry, equally spaced. The other thing that has that shape is the Mercedes symbol, if you can think about that one, or peace sign. Each of those are, well, more the Mercedes one. Same idea. Now, the last one on this diagram would be the third one, namely the oxygen on the end. So the oxygen on the end has how many bonding domains? Well, there's 2 bonds to left and the right, and electron domains is a total of the bonding and the non-bonding electron domain. And so we'll add to that the 2 lone pairs, the non-bonding domains. And so for a total of 4 electron domains, again, same thing, you keep seeing these patterns, they're not very surprising, I hope, by now. And 2 lone pairs and 2 bonding domains means we have a total of 4. And the 4 domains gives us, whoops, my tool didn't put the number on the way I hoped. Here we go. It's going to give us the 109-degree bond angle again. Now, in this case, we have 2 bonds and 2 lone pairs, so which is the geometry that corresponds to that? With tetrahedral electron geometry and 2 lone pairs and 2 bonding pairs, this portion of the molecule is described as having a bent molecular shape. Please laugh at my tool. My tool is being very stupid today. All right. Now, one more thing or two to think about. The diagrams that relate to these things from your textbook look like these. They have exactly the same information in here with some specific examples. They talk about things in terms of charge clouds, which is the same thing as domains. And so don't let that fool you. It's the same idea. So we're looking at bonding and non-bonding domains, and then compare it to the total number of electron domains. Clouds, domains, same idea. And so don't let that fool you. Sometimes that word bothers people. And so when we're looking at this chart, it's exactly the same thing we were looking at the end of the chem activity at the start of this mini lecture. There are examples for each of the geometries that we described. So the bond angle is the angle formed by 3 adjacent atoms. You always have to have 3 atoms to get an angle. When you have 2 charge clouds, when you have 2 charge clouds, they're going to be farthest apart because electrons are repelling each other when they point in opposite directions, and you get a linear geometry with a bond angle of 180 degrees. We've already looked at carbon dioxide, which has that structure, and HCN, which is hydrocyanic acid, also has that structure. 2 bonding domains, doesn't have to be single bonds, and no lone pairs, gives us 180-degree geometry and a bond angle and linear geometry. The next option is 3 charge clouds. They're farthest apart if they lie in a flat plane, and that becomes like an equilateral triangle. The geometry is trigonal planar for the electrons, and their bond angles are going to be 120 degrees. If you don't have any lone pairs, such as shown at this top example and the one we already did at the end of that, the POGIL exercises, you just have 120-degree angles, more or less. Notice there's some distortion here. And if you have instead 1 lone pair, as in shown in the SO2 molecule, again, we will have 120-degree angles close to it. But if one is a lone pair, the molecule is described as bent. You can't have a triangle when there's only 3 atoms. There are not 3 things attached to the central atom. All right, the last choice then is for 4 charge clouds. 4 charge clouds extending as far apart as possible from each other because of electron repulsions. The electron repulsion theory has a name. It's called VSEPR, valence shell electron pair repulsion is the name for that. And they're pushing each other as far away as possible. You'll find on Mastering Chemistry a video about that if you look. But you get a regular tetrahedron with bond angles of about 109. The shapes are going to be varied depending upon the number of lone pairs. Without any lone pairs, it's tetrahedral. With one lone pair, it's pyramid, trigonal pyramid, or bent if you have two lone pairs. Lone pairs repel strongly, and they will distort things, giving you slightly different bond angles, as you've already noticed by now. All right, one last thing to comment. There is a section in the chapter that describes elements that are known as diatomic. They always occur in pairs. You should be able to draw their Lewis structures, counting up their valence electrons and not thinking too hard because there's only two atoms, and they're worthwhile to try. But they're simply elements that you're going to need to know that will be always occurring in pairs. When you find them in examples in reactions in later chapters, nitrogen is always in pairs. Oxygen is always an O2 molecule, or fluorine is always 2. We call this diatomic. The way that I was taught to remember this, and everybody has a different one, is to think in terms of the elements and a way to remember them. Where they are on the periodic table is a pretty good suggestion, because there's hydrogen, nitrogen, and oxygen, and then all of the halogens, everything in that column. And my high school chemistry teacher liked to think of it as being a military title, because it's the Honorable First Class Bryat. Well, the last element down here is astatine, and it just fills out the pattern, although astatine is an extremely rare element. But at least it makes a point, and it makes something pronounceable. You just need to know them. Put them on your note card, then you'll be sure. But whenever they show up in chemical equations, they will always be diatomic, never singly. All right, don't forget, don't go through life one electron short of an octet. Make sure you study chemistry. Good luck working on your homework.